In class, we saw that when we were looking for the reverse of the derivative, it's equivalent to looking at areas under a graph. And the challenge is that if the shape is not a simple composition of things that we know the area of, we're in a bit of trouble. So what we're going to do is start off with an estimating procedure, and then we're going to see if we can generalize that to something that works in more cases. So suppose we had this curve here. It is definitely not something that is made up of straight lines or circular areas, so we really don't have that much to work with. Let's talk about the region, though, that we're trying to get. In principle, we're looking for here, in the question, the area under the graph between x equals 1 and x equals 4. So this region here. We're going to call that region A, and so it has some kind of area. Now what we can do is make a rough estimate of the area simply by putting a rectangle around the whole thing. So let's go from here to here, and there's the peak that we hit at 4. And if we imagine calculating the area there, well, that green area is going to be 3 and the base times 4.5 on the top, which is the height. And so we're going to get 13.5 square units. Now, let's be careful here. This is the rectangle area. Let's call that B. And that's certainly going to be an overestimate of the actual value of the area under the curved part. In fact, we have all this extra region up here that we don't really want. But it's an estimate. On the other hand, we could also draw this rectangle here, and in that rectangle we have, let's hide the other part for a second here, we have this extra area here that we want that is not part of the rectangle. So this area here, let's call it C, is definitely going to be smaller than the area that we really want under the curve. And what can we do about C? Well, we can actually calculate C. That's why we like it. It'll be 3 for the base times 1 for the height, and that gives us 3 square units. So what we can say next is the area that we really want, the curved area, which is hard to find, can be bracketed by 3 square units and 13.5 square units. Now that admittedly is not a very narrow window. 3 square units to 13, that leaves a lot of room. So what can we do to take this fundamental approach and make it more accurate? Well, one of the key ideas in calculus is to take limits and use smaller and smaller pieces, and that's exactly what we're going to do here. So what we're going to do is take that same interval of 1 to 4 and divide it into sub-intervals of width 1. Let's see what that looks like with the underestimates. We're interested in this entire interval from 1 to 4, but we're going to look at it on a segment-by-segment basis with rectangles of base 1. Now in this interval here, this is the region that we want to capture. But if we want a simple underestimate that we can get an area of, we draw a rectangle here using the lowest height available, which is height 1. On the next interval, we can be a bit more aggressive in our area, and we get something of height 3 that's still lower than the area under the curve. And finally, on the last interval here, we can take an underestimate again, and all of that gives us an area of 3 rectangles that's going to be less than the area underneath the actual curve. And if we do the calculations of base times height, we have 3 rectangles, all of base 1, and 3 different heights for each of these rectangles. And we end up here with a total of 8. Now that's already better than the estimate we came up with last time using wider rectangles, so it feels like we're going down the right path here. We can repeat the same operation, except this time overestimating. And when we do that, we again get a much narrower limit on, or upper bound on, the area we're looking for. Here, if we do base times height on the first interval, we would use 3 as our height. Then on the next interval, we'd go up to 4, and that's an overestimate of the area under the curve, which is what we care about. And then on the last interval, we would use 4.5. And if we do that, we get 3, 4, and 4.5. That's 11.5. And now we see that this is a much tighter band or tighter range for A. We still don't know it exactly, but it is certainly in a much narrower range, and we can get a much better estimate of what the area under the curve is. The key calculus idea that's hiding in here is that we can repeat this process for any number of rectangles. And when we do that, we can imagine that we're going to converge towards the actual area. When we talk about these methods, say we had that curve again, we're going to give a name to the specific approach of taking the left-hand point on some interval, and on some interval taking the left point and using that as the height of our rectangles. We're going to call that left of n, where we use n rectangles. So in the last case, what our previous example was, or what it illustrated was, left of 3. And we also did, at the same time, when we did the overestimate, we did the comparison with the right with 3 rectangles as well.